Okay, so let us start our discussion on vibrational spectroscopy, and in particular the two vibrational spectroscopy that I am going to discuss is Fourier transform, infrared spectroscopy and Raman spectroscopy. These are two concepts that I am going to, and where are we going. So, in this, if you remember, we have started discussing with Jablonski diagram, right. So, Jablonski diagram is like in the electronic level, between the electronic level you have various vibrational levels, and in vibrational level we had a rotational level. Now, if you compare the energy gap of the electronic state versus vibrational state, it is a very different. So, therefore, the energy that is required to excite this vibrational state will be comparatively low. So, if we are exciting electronic state using UV visible light, for us it is a infrared is enough. Infrared energy is less, wavelength is high, right. So, we can excite essentially these vibrational states that are there, and here is the infrared spectroscopy, like you can do in this wavelength 10 to the power minus 6 to 10 to the power minus 4, and frequency is 10 to the power minus 6, like 14 to 12, that is where we can do the infrared. So, this is the level that we are intending to excite, the vibrational level using infrared spectroscopy. And where this vibration is coming? Vibration, right, its name says vibration. हो कहाँ रहा है vibration? In the bond. Nucleus अभी NMR तक रुक जाते हैं. It's a electronic, all are electronic spectroscopy. So, here is a nucleus, here is an atom, here is another atom, two atoms, nucleus sitting quietly in the, and there is an electron cloud. That electron cloud vibrates. That's create, like if you remember your 12th class physics, harmonic oscillator, it has a frequency, right. If you remember that 1 by 2k whatever mu you have, the harmonic oscillator, right. So, it oscillates and you can find the frequency. Similarly, here between two atoms there is a electron cloud which vibrates, and that give rise to this spectroscopy, wonderful spectroscopy called vibrational spectroscopy. So, we excite it here, and in vibrational spectroscopy what we are exciting by infrared spectroscopy, and each group, each functional group is very sensitive to particular kind of frequency, because that group, functional group, if you remember a little bit of your 12th class chemistry, CO, which is what is the functional carbonyl versus COH versus COOH versus CHO, aldehyde, ketone, ether, alcohol, acid, they are different functional group. And if you look at the electronic cloud around them is also very different, right. CO has a different electronic cloud versus COH, and therefore, their vibrational frequency is very distinct, and this vibrational frequency actually, this distinct vibrational frequency has a particular range where they give it, and that gives the molecular signature in this IR spectroscopy, and therefore, FTIR is called fingerprint spectroscopy for a chemical molecule. Fingerprint, right, now all of us are remember, तुम्हारे fingerprint से ही gate खुलेगा, that means your fingerprint is unique, right. If you are only authorized, you can put your finger and gate will open. Similarly, OH has a fingerprint, some with little variation, that is what it is going to come. CO has a fingerprint, COOH has a fingerprint. So, all of these has a fingerprint spectroscopy, and we can use FTIR to probe the functional group, right. So, its probe characteristic of various functional group, and it is like if you compare now with UV visible you cannot find it out, ketone tha, aldehyde tha, ether tha, ester tha, you cannot, right. You get it, it is a chromophore or not, but if you combine your UV visible with FTIR, you know that here is my functional group, right. Aldehyde, ketone, ether, ester, all of these you can find it out. It helps in getting it your this very correctly. only problem with FTIR is that water absorbs hugely. Water concentration is huge, therefore it absorbs hugely. So therefore, for all practical, say biomolecule will come to in a moment, but chemical molecule you can dissolve in any other solvent, chloroform may dissolve kar do, DMSO, you can still do it. For biomolecule, it is a difficult because it has to be in water, right, and water concentration is very high. So if I record FTIR using watery sample, only problem is that water is dominating hugely and therefore you cannot get much spectra. So uske liye there are some tricks which I am going to discuss with you, but for chemical molecule identification of functional group is extremely easy, and therefore when suppose your friend he is working in a synthetic organic chemistry lab and he organize after 5 step of reaction, he will go and do what? UV visible लेगा, IR लेगा, NMR लेगा, proton and carbon NMR mass लेगा, and then he can identify whether his reaction is going in right direction or not, right. So synthetic organic chemistry does 20 step of reaction, 15 step of reaction, her step per your end product should be correct, and these techniques help you to know that you are on correct track or not correct track. Now, biomolecules, it is already synthesized by the bacteria, right, or any organism, yeast or insect or human cell. Here you can use this spectroscopy to identify whether this protein is in right condition or not, but water is a problem. So what can we do? Water is a problem because of, so you can use the D2O, D2O has a different frequency, chloroform. If you do not want to do is, there is another method called put your biomolecule in a KBr. KBr you know, potassium, that does not absorb. So you put it, mix it, make a solid thin film, put it in the FTIR and you can record it. But nowadays with improvement of the technology, new machine has come, FTIR ATR, or the liquid cell has come. Now Bruker and Simajo and all those has made a liquid cell where you can put a drop of your protein and still you can do it. So technology is advancing day by day. Even water is a problem, but we have to get rid of water by technology and we can do the protein sample in FTIR, right. So we already discussed this, what is IR active and what is not IR active. So why IR active के लिए क्या चाहिए? It has to be dipole होना चाहिए, right, dipole होना चाहिए, and we can also find it out how many vibrational mode we have. Simple formula is 3n minus 5 or 3n minus 6, n is a number of atom. So CO2, or let us start with a CO, how many atoms we have? 2, 3n minus 5 or 6. For a linear molecule, right, 5. So only one, बस ऐसे ही खींचा जा सकता है. HCl similarly, right, but CO2, it's a linear 3. So 3 multiplied with 3 minus 5, right, 4 vibrational mode we should have. उसमें कौन एक्टिव है कौन नहीं एक्टिव है, we can see it subsequently. If it is non-linear like H2O, it will be 3n minus 6. So 9 minus 6, that is 3 vibrational mode we have, right. So we look at what are those. So here is our CO2 molecule, CO2 4, right, but एक में क्या होता है कि both are pulling, that dipole is not getting created because equally it's a pulled. But other thing like if it is asymmetric stretching, एक ज़्यादा एक कम, dipole is created, bending dipole is created. So all these are FTIR active, right. Here water molecule, it's like a, if motion is happening like this, stretching like this, rocking like this, so all of these will be FTIR active, and you can find it out what is active and what is not active. So CO has only one mode, it absorbs in IR. CO2, the main like a symmetrical stretching does not, but others mode absorb, and this is a kind of motion you have, you can visualize. So CH2 group, it's a 3 atom, right. So you can do various of wagging, twisting, asymmetric, symmetric, scissoring, all sorts of motion you can have, and all these are the motion which is creating the vibrational frequency. Therefore they correspond to a particular frequency which is signature of a functional group, right. CH2 is a functional group, you can have it. So, based on that, people have done extensive research to find it out what is coming where. So, it is for covalent bond, you can find it out the region around say 1000 centimeter inverse, and also I told that FTIR is centimeter inverse, the frequency, it is a wave number that is represented. So, you have a like a single bond, then you have CC bond, CN bond, CO bond coming in 1400 to 1800, then you have triple bond, C triple bond C, C triple bond N, then you have a CH frequency and NH frequency and OH frequency. These are typical frequency range of a functional group that comes, right. So, that is a FTIR. So, you can find it out of any molecule which is corresponding to what, right. If our molecule is like this, what is this? Famous molecule, ethanol, right. So, ethanol has one CH stretching, you remember CH stretching was around 3000. So, it has 3001 to 2850. It has a CO stretching which is 1200 to 100 centimeter inverse, and then OH stretching, that is a water also has a there 3700 to 3000. COH bending, you have a frequency 1500 to 1200. So, these are typical frequency that you have from the ethanol, and you can find it out what is there. So, based on that and after lots of research, people find it out which functional group is going to fall here, and this is the table that represents the frequency, the IR frequency of each of these frequency, like each of the functional group. Like so for CO stretching, it is a 1000 to 1200 centimeter inverse. CH rocking, NH rocking, it is a 650 or 625 to 800. NH bending 1500 to 2000, right. Now, CO, can you see CO somewhere? CO stretching 1500 to 2000. So, can you now looking at this, can you differentiate between aldehyde and ketone, right. It is a similar functional group. So, if your CO is coming there and COH somewhere it will be, CH is 1 and COH should be like a CO again can be in a similar one, but since H is attached it will shift it because the electron cloud is. So, between aldehyde ketone, between aldehyde acid, alcohol, you can find it out, and these are used for identification of molecule, right. So, important point is it is for some traditional region we interpret or we just report the IR frequency in terms of 1 by lambda. Lambda is wavelength, wavelength is in meter, nanometer, centimeter. So, it is a 1 by centimeter inverse, right. That is we call it the wave number. So, unit is centimeter inverse, and then we can put it like a the IR in terms of speed of light. If you put it just frequency also you can find it out. So, traditional region it is just centimeter inverse, it is not any particular region. Typically IR has narrow line for many of those, and we can identify something like this if you look at. And as I was saying, between ketone and aldehyde, if there is a hydrogen bond, electron shifts, and therefore you can find it out whether whether the hydrogen bond is happening or not, right. So, if a molecule is forming hydrogen bond, you remember this, a molecule is forming hydrogen bond, IR can differentiate whether it is forming hydrogen bond or not. So, think little bit where you want to differentiate hydrogen bond formation. IR can differentiate whether the molecule is having hydrogen bond or not. Yes, where hydrogen bond formation happens? In protein folding. So, when it is random coil like this, there is no hydrogen bond. If it forms a helix like this, CONH, hydrogen bond. So, from random coil to helix formation, you clearly see a shift happening in the IR frequency, and you can easily just doing a simple IR experiment you find it out. Now, my protein is in alpha helix condition. Now, when it forms the beta sheet, also you see a hydrogen bond, but helix ka hydrogen bond and beta sheet ka hydrogen bond is going to be different, isn't it? Do you think it is going to be different or same? कैसे?
हाइड्रोजन बॉन्ड्स का एक्सटेंट चेंज हो जाता है,
एक्सटेंट चेंज हो जाएगा, इलेक्ट्रॉन क्लाउड चेंज हो जाता है, तो इसके लिए उसकी शिफ्ट अलग होती है. सो नाउ दिस इज द ब्यूटी ऑफ नाउ FTIR, that if the same CONH you observe, CONH, if you observe, it can show a shift when it is in random coil state versus helix state versus beta sheet state, and that is used in biology for finding it out whether my protein is in folded state, unfolded state, whatever beta sheet state, alpha. And this is what we are looking at here. Which moiety we are looking? CONH, right? CONH. So we are sitting at CO frequency and NH frequency. What is CO frequency?
1700.
Very good. 1700, 1600 to 1800 CO frequency, ketone, right? 16 to 1800. If I sit at that frequency and just monitor whether the change is happening or not, I can find it out the secondary structure of the protein. So this is the one way to find it out, confirm the secondary structure in a protein. No fancy experiment, just simple FTIR. Just simple FTIR, we can find it out whether the protein is in alpha helix state, random coil state or beta sheet state, right? And another is NH. So three important band chains are seen in the protein from the backbone. We are not even talking side chain, just backbone. CONH is in the backbone hydrogen bond formation. So NH stretch, amide 1 which is called CO, and amide 2 CNH bending, right? So if you just look at NH stretch, that's 3290. In sheet it is 3280 to 3300, and in random coil it's 3400. Most of the time we use this amide 1 which is CO stretching. 1650 to 1660 it's a helix, 1630 it's a sheet, and 1680 to 1700 it's a random coil. So if you look at some shift of 20-30 cm inverse is telling me whether my protein is in helix, sheet, random coil. But एक बात बताओ, कोई भी ऐसा प्रोटीन होता है क्या जो कि केवल हेलिक्स हो, केवल रैंडम कॉइल हो, कोई केवल बेटा शीट हो? नहीं होता है ना, टिपिकली ऐसा नहीं होता है, मिक्स होगा. नाउ मिक्स होगा और तुम्हें क्या मिलेगा? एक फ्रीक्वेंसी. What you get is just one broad, like a generally typically little broad line. Now it has everything, helix, sheet, random coil, right? So that's a typically you get it. Now you have to do some mathematics to find it out what is that. So infrared dichroism is powerful technique for elucidation of a helix, sheet, random coil. I will come to that how you can do it, but in a helix you think hydrogen bond is forming just on top of each other, right? I will come back to that frequency again. Here in beta sheet, how does hydrogen bond forms?
One parallel and anti-parallel.
Like this or like this? Now hydrogen bond is shorter in parallel or anti-parallel? Likho hydrogen bond form anti-parallel. Good. Anti-parallel because they are like this, it forms like this. Parallel mein it's a tircha, right? So even if I don't go in detail, I know that hydrogen bond formation that is happening in a helix versus a random coil where it does not happen, versus a parallel beta sheet, anti-parallel beta sheet, electronic clouds are in different, right, different environment, and therefore their frequency in IR is going to be different, right. So that is used basically, therefore NH stage amide 1 is preferentially absorbs IR, amide 2 shows opposite behavior. So for beta sheet, the long axis of the structure is along the extended peptide bond, and peptide hydrogen bonds are perpendicular to that axis. Here is my long axis in beta sheet, peptide bond is perpendicular to this. In a helix, helix is like this, hydrogen bond is like this, right, it is a parallel, right. So therefore that is what is the difference that you have. So just look at this, let us look at how you can find it out. The free DNA also has a signature, the HSA bound DNA and HSA free HSA and HSA bound DNA. right. Now, do you see a change anywhere? Just left hand panel. Let us look at. I said that a structure is going to be different. First, let us look at this. DNA has some frequency, all these are frequency. Protein has some frequency. Which frequency I was interested? In this frequency, right? This frequency. Now, I mixed it both of these, just concentrate here only, right. If I just put it here, I mix DNA with a protein and I looked at here. You see there is something appearing on. What does it suggest? Some interaction is happening, some complex is forming. So, one can only see that some because of complex formation, some peaks is shifting and forming at 1300. Right. You can even subtract it and take a difference. So, just HSA DNA difference you can plot it HSA. So, like what we are doing, just increasing the concentration and plotting it the difference, and you can find it out, change is happening and that change is showing that these are forming complex. So, this not only gives us some structure, but also same thing you can do with a free HSA, free RNA and complex formation, right. So, basically it is not only give you secondary structure, but also tells you about if complex is forming, you can find this shift in the IR frequency and you can elucidate the structure.